Alright, so I have a playlist for CFG, context-free grammar, and context-free language is the way that we are looking at CFG from a different perspective, from the perspective of theory of computation. So my playlist for context-free grammar is more about how we can use it for natural language processing and the ambiguities of natural language. But in this lecture, I'm going to focus on the perspective that is related to theory of computation. You know, we have regular languages that those you can implement it with finite state machine, but sometimes that is not enough. I mean, some languages you should go out, you should relax your constraint, and we call them context-free languages, and those are implemented by finite state automaton. And sometimes even that is not enough. You should relax some more, because some languages are in this points that are not even context-free languages. And finally, Turing machine, non-Turing machine. So you extend it from regular to different regions. So this lecture we focus on CFL. I mean this region, and you will see what is a context-free language. Your brain acts like a language recognizer. For example, when you say that, for example, you recognize that the cat is in the hat. The cat is in the hat. So the sequence is correct. You understand. You accept it. You accept this sequence because it sounds logical. I mean, it recognizes the grammar is okay. But when you say hat the in is cat, you know something is missing, something is not correct, the sequence is not correct, so you reject it. The same thing we do it in theory of computation. When the state machine accepts something, it means that it is okay. It is something that my mind understands that. I mean, grammatically is correct, semantically is correct. And also the brain is like a language generator. For example, why you would want to do so and how you manage to do. For example, language, we generate something. And such a device begins when given some sort of start signal to construct a string. Its operation is not completely determined from the beginning, but is nevertheless limited by a set of rules. Eventually, this process halts, and the device outputs a complete string. Okay, for example, a regular expression is a language generator. For example, we can implement it with some finite state machine. For example, we are in state Q1, and we have some input, call it A, and then we are in A, so it becomes A, and suddenly you go to another state by giving it B, and then you go to state Q2, and you state in B. With B2 input, you stay in Q2, so it becomes B, and so on. So this is like you don't need memory for that. You don't need stack for that. You can implement it with a finite state machine. So first an output A, and then you either output a number of A's or output a number of B's, and finally you output a B. You stay in B forever. And so you have implemented this regular expression. You see, you don't need any stack. Stack helps you to some kind of having a memory. But for regular languages, it's very simple. That's why regular languages is here. But sometimes you have CFL. You should go context-free language, because you can. Sometimes there are something that you need some context-free grammar and finite state and push down automaton to implement that. So you should enlarge the class of the languages that can be implemented, and that's why context-free grammar is what you need. For example, S could be A and B, and M replace M with A or B, like here. So it becomes AAB. And for example, replace A with empty string, so it becomes AB. So AB is in your language. Another thing could be A, for example, AAB. So you can cover all of the strings in your language with just some rules. We call these things some rules. Rule 1, this is rule 2, rule 3, and sometimes your rule goes to empty string. So you replace A with E, empty string. And sometimes you replace A with some imp A and then some symbol A. And these are the rules that you need in order to create the strings of your language. For example, your language is just a very simple regular expression like this. As I said, you can generate this with this context-free grammar as well. Another example, for example, to generate a string AAAB, for example, we are in state Q0, and we have inputs A, so A, the second one again A, the second one again A, and then you should know that you should go to B, for example. So if you have input B in your tape, you go to state Q1. So let's think about it. We apply the rules. As I said, in context-free language, we have some rules. So we replace S by A and B. So this is what you want. And A and B we can apply. So instead of M here, I want to replace it with A. So it becomes AAB. Then we have another rule. This is another rule. So instead of A, let's call it AA. A is here, so it becomes AAAB. One more time, because we have 3A here. So one more time, again, we use this rule, and it becomes AAB. So 3 times A, and finally, you replace A by E, empty string. So all of this becomes AAAB. And this is what you wanted. So this string is inside your language. So you see how we use context-free grammar to see whether this string is inside our language or not. And this is how context-free grammar is beautiful. It's a language generator that operates like the one above with some such set of rules. Let us pause to explain at this point why such a language generator is called context-free. Consider the string AAAB, which was an intermediate stage in the generation of AAAB. It is natural to call the string AA and B that surround the symbol A the context of A in this particular string. Now we apply this rule, says that we can replace A by a string AA, no matter what surrounding strings are. That's why we call it context-free. We don't care about the context, we just apply this rule. No matter what the surrounding strings are. In other words, independently of the context of A, we don't care what kind of things are inside A. As long as it is A, we are okay. We don't care. We just replace A with A and A. So you see how we can relax CFG constraint and we go to context-sensitive grammar and more things, and then neural Turing machine, and then so you enlarge. You relax your constraint in order to cover more and more languages, because in general a language could be very, very general without any constraint. So a context-free grammar is just a set of alphabet. We have a set of terminals. In terminals, for example, in natural computational linguistics, we know those terminals are, for example, part of speech tags, if you have seen my playlist for context-free grammar. Or R, the set of rules. We use some rules. For example, S could be to go to AS. Or these are these kinds of rules. Or A go to empty string. This is another rule. And then we have S, the start symbol. Just like finite state automaton, we need to start from some state. And so another example, when the grammar to which we refer is obvious, we write A goes to W. And so we call any sequence of this form a derivation in your grammar. However, this sequence may be any strings in V star, and the length of the derivation may be any natural number, including 0. We also say that the derivation has n steps. Another example, we have this beautiful rule, we have two beautiful rules, and this is a possible derivation. First, we replace S because of this rule number 1, so it becomes ASB, and then we apply it again. So again, instead of S, we call it ASB, so this becomes this. And then we use rule 2, so rule 2 is here, applied with empty string, so ignore this, it becomes AABB. So now you see this is like A2B2, and this is the language in general. You can work on that. And okay, this is the end of this lecture.